Okay. Yeah, so let's restart the lecture on astroparticle physics. We are on the subject of dark matter. If you remember, last time the story was like this. So before last time, we tried to look in the early universe. We saw that, well, there are some indications that dark matter exists already in the early universe. Then we tried neutrinos. That didn't work. Last time we started from modifying the model of neutrinos, considering neutrinos that are very massive. Still, they had a chance to be in thermal equilibrium in the early universe. And then little by little, they decoupled. Then they settled into some cosmological background of, it would be not neutrinos, it would be weakly interacting massive particles, WIMPs. And then they may form the totality of the dark matter, even more than this, depending on their cross-section. If the cross-section is, I'm not sure if it's not like this. If the cross-section is 10 to the minus 25, sigma cross-section times velocity is 10 to the minus 25 centimeter cube per second, then the density of those weakly interacting massive particles in the present universe would be about the critical density, right? It would be even too much, so the cross-section should be a bit lower. Okay, so that was one part of the lecture, and the other part of the lecture we were looking at complementary evidence for dark matter from galaxy clusters, from spiral galaxies that rotate. We can measure the matter content of those objects by looking at velocities of constituents. And then using either virial theorem or just the Kepler law of rotation, we found that, well, the total mass of nearly all galaxies and galaxy clusters is much larger than the mass that we can account for looking at stars, or in the case of galaxy clusters, it was hot gas inside the objects and so on. So we also looked at our own Milky Way. Then we found that measuring the rotation velocity of Milky Way disk as a function of distance, we can reconstruct mass contained within some volume, right? And that was the result. It's one of the recent papers which derives the mass like this. So these lines, the colored lines, they are mass within the known types of matter, stars and gas. And then, well, this mass is not sufficient to account for the rotation velocity. So we have to add something to patch the calculation, to add some dark matter. That black line is the best fit dark matter mass within some distance. On occasion, it is modeled. It's, well, we don't fit point by point, distance by distance. We try to fit the whole range of distances, well, assuming certain density profile of dark matter. The most popular one is called NFW, Navarro-Frank-White. It was a function like this. It was a function like FW. It was something like 1 over R, 1 plus R over R0 square. So the function interpolates between, if I plot log n versus log R, it is an interpolation between a profile that is 1 over R and 1 over R cubed. if I integrate n like this, 4 pi r squared dr, of course, I get some finite mass, right? Well, if this function would continue as 1 over r, that would be good. So, well, the function is reasonable. And, well, one can find a fit to the data. But, well, actually, if we look within somewhere, maybe, well, within the solar radius, well, the sun is at the position of this vertical line, 8 kiloparsec away from the center of the galaxy. And we can see that, sorry, the colored line is the dark matter modeled with Navarro and Frank White, and black line is the usual matter. So we see that within the solar distance, it is the usual matter, the stars that dominate the mass content, right? And since this component is subdominant, it is difficult to measure. Well, the uncertainty is too large. So people try different models. Sometimes they even try a model that is called cohort profile that goes to constant within solar radius. Yes. So we can consider this as a range of uncertainty, in fact, because different models fit the data. But we see that if we go to the outskirts of the galaxy, maybe to, I don't know, 30 kiloparsecs distance, the mass of the dark matter is already much larger by a factor of at least 3 or more than the mass of the usual matter. Okay, that was the previous lecture. So for this lecture, what I want still to stay on the dark matter. We looked at the possibility to see some signals from these WIMPs or whatever other, well, we didn't consider other models of dark matter, but there are many of them. So we tried to look at some signatures of WIMP in whatever data. Today, I will try to look at the possibility to catch those dark matter particles in laboratory. And then I will come back to astronomical methods. So for laboratory, what matters on this plot on the right bottom is that around us, at the distance 8 kiloparsec from the center of the galaxy, the overall density is whatever level, some 10 to the 10 to the 4 times 10 to the 10 solar masses in total, yeah. And then, no, well, it is perhaps twice this, because half of the mass is from usual matter, half of the mass is in the form of dark matter. If we do an estimate, we divide this total mass by the volume. It gives us a characteristic density scale, which is sort of, well, 0.3 giga electron volt per centimeter cube. This is mass divided by 4 pi r, 4 pi over 3 r cube. Well, this is one thing that we can use. And then if we directly look at the, we know what is the density of dark matter particles. We know what are the velocities with which they are moving. What would be these velocities? So our galaxy rotates with velocity about 200 kilometers per second. This is Keplerian velocity. The dark matter does not reside in the disk because it does not dissipate angular momentum and so on. Yeah, so it stays in a halo, more or less spherically symmetric. It forms virialized gas. Then, well, the virial velocity is more or less the same as Keplerian velocity, so we can safely assume that dark matter particles are moving with the speeds of about 200 kilometers per second. And then, well, if we know the mass of the dark matter particle, let it be 100 giga electron volt, We know that within this room, in every through every square, well, within every cubic centimeter, there is a sort of 10 to the minus 2 of those particles. So maybe one particle per 10 centimeter cube. And these particles are crossing the room with the speed 200 kilometers per second, right? So how do we detect them? If we want to see them, we need to make them bump into something, right? That's how we feel the particles. And of course, well, we don't have much choice. This something has to be atoms or atomic nuclei. Well, it depends, right? So we need some detector that would have a sensitivity to the signals. Now, to these bumps, yeah? So what is the basic effect that we are searching for? If this is a dark matter particle, well, if this would be, by the way, a neutrino, maybe a process like this is possible, that we know that neutrino, when it interacts with matter, it can interact in two ways. It can either just bounce elastically. In terms of particle physics terminology, it would be called neutral current reaction, but it can also change identity. It can, let's say, muon neutrino can be converted into muon, right? That is an interesting possibility. But for the dark matter particles, maybe they do this, by the way, because our assumption that they participate in weak interactions. They maybe can change identity of atoms or elect of, well, change identity of atomic nuclei or something like this. Well, this is more model dependent than a simple reaction that is an elastic bounce, right? So what people try to do is to look at the reactions like sketched on the left. So those are the colored zinc is atomic nucleus, right? And then dark matter particle arrives at the nucleus with velocity 200 kilometers per second. It bounces, so obviously it would transfer some energy to the atomic nucleus, right? We can even calculate how much energy would be transferred. If we take, well, the kinetic energy of the particle, so we know the mass, we know the velocity, right? We can estimate for a particle with the mass about giga electron volt, it would be a fraction of kilo electron volt, the energy involved in the reaction, okay? So if we take 100 GeV particle, it would be already 30 kilo electron volt energy transfer. Is this detectable or not? Well, that's the question. So is it a lot or is it a little? It is, does anybody have a feeling what is kilo electron volt? Well, we need something to compare with, right? So, and once, well, there are scales that are rest energies of particles, right? Rest energy of electron is, yes.
511.
What? Of what?
Kilo electron volt.
Kilo electron volt. 511 kilo electron volt. So it's a fraction, a small fraction of the rest energy of electron, right? For proton, the rest energy is giga electron volt. So if somebody bumps with kilo electron volt, proton will not fly away, right? Relativistically. Electron might already get a significant kick, right? Then if we talk about the scale of, well, we also know other particles in this room. Let's say, what is the typical energy of molecules in this room? How can we know this? Molecules of the air. How do we estimate energy? we know the temperature, right? What is the relation between temperature and kinetic energy? If I want to know the energy of molecules of the gas, well, I would write 3/2 K Boltzmann T is about the kinetic energy, right? That's for the gas. If I take 300 Kelvin, so K Boltzmann is something like 10 to the minus 4 electron volt per Kelvin. If I take 300 Kelvin, that's the temperature scale. It gives me an energy which is it is 1.03 electron volt, right? So kinetic energies of molecules in the room are small. So if a dark matter particle bumps into an atomic nucleus here in this room, it's a significant impact, right? Well, molecules don't do this, right? So we would notice this. That's an interesting effect, right? Maybe that's the simplest way to build the detector. We just we need to know how to spot a kick, enormous kick of maybe 30 kilo electron volt. Then we are there, yeah. Maybe that's an idea. Otherwise, would we do this in this room? Would we? So would we? Well, suppose that we have a method to spot a kilo electron volt kick. Would this be sufficient to, well, to claim detection if we put a detector, whatever, with whatever detection method in this room? Think about whatever noise that is possible. Yeah. So molecules of the air, they move slowly. They don't do kicks of kilo electron volt. Can anybody do anything? Do a kick of kilo electron volt on the molecules in this room? Those are there particle physicists here? Yes. Did you hear about cosmics? Right. So there is a lot of particles that are passing through this room. Most of them are muons at the sea level, right? But those are particles produced by cosmic rays penetrating in the atmosphere, producing, we discussed briefly, right? This extensive air showers. So a lot of particles are passing through this volume, and typically those muons are particles with enormous energy. I don't know, 100 of giga electron volt or something. So when they pass through the room, they go from top to bottom without losing a lot of energy, and they kick the atoms here and there, and there is a lot of them. Yeah? So in fact, even though the air molecules are not moving fast and not transferring kilo electron volt here and there, they systematically are affected by this kilo electron volt and larger kicks. Yeah. So there is too much noise here in this room. We need somehow to screen the detector from this noise. What would we do? How can we screen from those muons? Yes.
It's underground.
Yeah, we go underground, right? If we put this under a layer of rock, then even muons would be, well, already at the level of the sea, well, somewhere in the middle of the atmosphere at the altitude of 10 kilometers. Actually, it's not the muons that are dominant particles from cosmic rays. These are electrons and positrons. But electrons and positrons, they like to interact. They are absorbed by the atmosphere. We are protected from them, right? Then if we go under the rock, we would be also protected from muons. So we need some low well, for us, this muons or electrons or whatever, this is background, right? So we need some low background environment. We go into the rock, right? So then our goal is to detect this kilo electron volt kicks. Then if we think about detection methods, what let me not show this, let me ask him. So now, how would we detect a kilo electron volt? Do we ever detect, by the way, kilo electron volts somewhere? Kilo electron volt, just in case, it's the energy of X-rays, right? So when we go to an X-ray scanner, people detect kilo electron volt photons, right? Somehow. Then maybe speaking about detection methods, if we have an atom and imagine that something bumps into atomic nucleus and kicks it with kilo electron volt, what would this kick do on an atom? Well, an atom is a nucleus and a nice stationary cloud of electrons, yes? Yeah.
Ionize the atom?
It would ionize it, right? Why do you have a feeling that it would ionize it?
Because I think that X-ray wavelength is like allows to interact with the nuclei or the electron.
Yes, that's one thing, right? That's why it would rather, well, that's why X-rays like to interact with nuclei, right? Because the wavelength is small. So it is, well, actually the wavelength is about the size of an atom. Well, if we take visible light, the wavelength of visible light is so large that, well, it would even notice an atom, right? Because within one wavelength, there is a lot of atoms. So the only thing that visible light can do, it can make atoms oscillate coherently. And that's why, well, when they do this, they start to deflect the light, because when they oscillate, they emit electromagnetic waves. So the overall effect is deflection, refraction of light, yeah? X-rays would rather target an individual atom. But then, no, well, you are talking about ionization, yeah? So suppose that I manage to kick exactly atomic nucleus. So what happens is my cloud of well, before I had a stationary situation where the cloud of electrons was centered on the nucleus, right? But now my nucleus is gone somewhere. Well, it's shifted, right? So the cloud of electrons would have to recenter, something like this. Yeah. Then if the energy of the motion is too high, some electrons would go away, yeah, because they would not follow. What is the typical energy scale involved here? If I shake an atom gently, they would all adjust, right? If I shake it violently, perhaps electron would be stripped away. What is the energy scale involved? The energy of ionization. Perhaps you have heard about at least one atom, right? In the course of quantum mechanics, everybody studies hydrogen, right? So the energy of the first level of hydrogen is minus, well, the energy of ionization of hydrogen is 13.6 electron volt, right? So for heavier elements, perhaps the energy of ionization is lower because they have more electrons on different levels. So the highest level of electrons is not very far from being free. Yeah. So it's called the first ionizing potential. It is typically in the range of electron volts, something like this. So here we are transferring kilo electron volt energy. This means that it's largely sufficient to ionize, right? If we ionize, what can we do to see this ionization effect? how do we see that something was ionized?
Like electric fields.
Yes, we apply electric field. Yeah, we put a battery and we put our detector in a sort of capacitor. Yeah, we do like this. So this is our detector. I would not take air. It's a bit too simplistic as a detector. Maybe something denser, maybe something of the density of solid things, right? But anyway, I would take a piece of matter and apply a potential difference like this, a voltage. Then, of course, if there is an electron that is freed, it would produce a pulse of current. Then if I put an ampere meter here, that would do the job, right? So I would see a brief pulse of current. Now, of course, it's a bit schematic, but it should be very sensitive ampere meter. Actually, it would be even not, well, my energy deposit is quite substantial, right? So I would liberate not one, but rather many electrons. It depends if I take, for example, silicium. That's the typical semiconductor that we take for whatever. It's the most popular material in electronics. It is a semiconductor, right? So what is the particularity of semiconductor is that, well, there is this valence band and conductance band, right? And there is an energy gap between the two. In silicium, it is about 1 electron volt. Yeah. So if I deposit 1 electron volt, if I kick this silicium with visible light, it would produce a pair of electron. And when I lift the electron to the conductance band, it would do a hole in the, well, it would produce a pair of electron hole. And that's what we use, by the way. We kick silicium with visible light here in the cameras of the phones, yeah? This is called CCD device, yeah, or CMOS camera in the phone. It is made exactly like this. So photons are, well, photons of visible light are particles with 1 electron volt energy. They are able to produce pairs of electrons and holes, and then there is voltage applied to the pixels in the camera in the phone, and we see pulses of light, pulses of current, right, in response to exposure to light. Yeah. Here, if I kick the same silicon or silicium, what do I say? Silicium, yeah, perhaps. So if I kick it with something that is kilo electron volt, well, I will at once liberate 1,000 of those electrons and holes, yes? It would be a nice pulse of current. So we can even use, well, a CCD camera to detect this stuff. Maybe we modify it a little bit, but the principle can stay the same, right? So ionization is a possibility, and then ionizations followed by sampling of current, right? That's one way to detect those dark matter bumping into material. Another possibility, think about, suppose that we shake an atom, but we don't ionize it. How does it work? If we have shaking electrons, what does it mean? When they want to, so we displaced the atomic nucleus, right? So now electrons, they are not in their initial.
Об этом говорится следующее. Электрон – субатомная частица, чей электрический заряд отрицателен и равен.
That's impressive. It was listening to me, this Google Assistant, or how is it called? Spontaneously. Yeah, so by the way, it was understanding English and responding me in Russian. Yeah, that's strange. So, yeah, so I have shaken the electrons. They are not in their initial stationary states, right? They are sort of, in terms of quantum mechanics, they are excited states, yeah? What do? They want to return to their stationary, to their lower states, right? What do they do when they do this?
Photons.
They emit photons, right? We can see this. If this piece of material is transparent for light, I can attach some photosensors. What are the most sensitive photosensors we know? I would sketch them like this. Again, I think, well, we have one particle physicist who had labs in laboratory. That's very typical. In particle physics, you sample photons, right? With what? Right, so the best material, well, we can also trick the chemical composition of material. We don't take material that in which photons are not good, right? We don't detect them. We take a material that likes to emit photons when it is excited. That would be scintillator. And how do we sample photons from the scintillator? Sometimes we want to detect single photon because, well, it's not a firework of photons inside. So we take, well, devices that are sensible to single photons. They are called photomultipliers, right? Have you seen photomultiplier? Tubes. So there are two types. There are vacuum photomultiplier tubes, and there are solid state analog of that. It is called silicon photomultipliers. Right, so in English, silicium would be silicon. Well, because as I told, the day before I teach in French. So in French, well, a couple of weeks ago, students were correcting me that I should not tell silicon, because in French apparently it's not silicium. So silicium is and silicon. It's the same thing, but in French you don't say silicon. Okay, so we can attach photomultipliers. We can choose the detection medium as scintillator, and we can look inside with photomultipliers, right? We can even combine the two, because this scintillator, it would be actually also, we can try to sample ionization signal from scintillator. It would be even better. You imagine that, well, our confidence in detection of this dark matter would be better, because we can look at coincidences. We could, so sometimes maybe the scintillator can do scintillation spontaneously because something happened to it, because somebody, I don't know, touched it. Or maybe it can do spontaneously a pulse of current because, I don't know, some thermal excitation happened inside, right? But if we look at a signature like this, we see a flash of light and pulse of current simultaneously. That's better, right? We can also look at the characteristic energy deposition. We can measure energy deposition 2 times, right? The strength of the pulse of current would tell us how many electron hole pairs were liberated, yeah? We can convert this into energy of particle. And then in scintillation, it's also the number of photons emitted is proportional to the energy deposition, something like this, right? So we can compare the 2 signals and take only those that are consistent with each other, that give us some right amount of, well, the same amount of energy, right? There is also a third effect that I would just, I would not try to provoke you, I would just explain what is this. It happens that this material that we would take, let's say if it is an atomic lattice, and now let's try to sketch the atoms on the lattice. Then imagine that there is this dark matter particle that bumps this atom and it kicks it in this direction. So what would happen to the lattice is that the lattice would respond, right? Well, the atom would like to return back, but it will first shake the neighboring atoms, and there will be sort of a sound wave traveling through the atomic lattice, right? So yeah, the sound waves traveling through material, they're called phonons. So we can try to sample this. We may do this maybe not sampling in each individual phonons, but well, if these phonons travel here and there, they would sort of redistribute energy between the atoms. They would slightly increase the temperature of material. If we have a very sensitive bolometer, this is the device that measures temperature, we might see that, well, if we take a tiny piece of material, maybe a single energy deposition in this tiny piece of material would raise the temperature by a fraction of a Kelvin. That's the third method. Again, ideally, we would take well, we would combine three methods together to get more handle on the signal, right? Then perhaps how would I distinguish a muon that is passing through the detector from a dark matter signal? A muon is a particle that would pass through the whole detector like this, yeah? It would produce maybe the same amount of, well, maybe it would deposit the same kilo electron volt, I don't know. But it would deposit it somehow differently. It would deposit it in a distributed way throughout the detector, right? So what I want also to see, I want to see some pulses that are very localized, some deposition of energy that is very localized. I need to somehow perhaps pixelize my detector. And then maybe measure these pulses of current like this pixel by pixel. Maybe well, the deposition here would make me this part of my cathode and anode detect the pulse current. Or maybe if I put photomultipliers everywhere here, I would see that, well, I can localize the pulse of current somewhere within the volume, right? Same for this bolometer thing. I would take tiny pixels and would measure temperature increase in a tiny pixel, right? If there was a muon passing through my detector, it would hit a chain of pixels rather than one single pixel, right? So these are three methods of detection of the signature of dark matter interaction: light pulses, current pulses, or temperature increases. And there is a variety of experiments that use three techniques in combinations. And again, as with example of dark matter, I pick up one example of dark matter model that was this weakly interacting massive particles. But well, I just mentioned that there is a sort of infinite landscape of dark matter models. Here again, I will take one detector as an example. Then, well, be aware that there is no limits to imagination of experimental particle physicists. They use machines of different sorts and flavors. So I will take one example that is called xenon experiment. By the name, you understand that there is something with xenon. So xenon is a noble gas, right? We know that, it as noble gas. What is special about noble, by the way? What are the noble gases?
Stable.
Very stable. Why?
They respect this.
The what principle?
I don't remember. They have this. I mean, helium has two electrons, and it feels a certain
Right, that's the,
layer of electrons, and then it's 8. I think.
yes. So you want to to add something?
We don't make molecules because their valence electron layer is full.
Mhm.
They usually can't make any molecules, so they don't interact with one another.
This I'm not sure. Xenon has a molecule, it's xenon 2. That's yeah, the xenon likes to bind into molecules. That's what I remember. Maybe I'm wrong, but in general, yes, the idea is right. So if we look at the atoms, they have layers, right? So there is innermost, next one, and next one. So every heavy element, it has more layers, and then metals are the elements where the external layer is almost empty, right? There is only one electron traveling, so it likes to bind with other elements, yeah? So then noble gases are elements to the right of the periodic table. That is not the periodic table. What is this? Chart of the nucleus. This is perhaps the chain of nuclear reactions there, but we don't see periodic table here. So they are to the right of the periodic table. They have the outer layer filled completely, right? There is no empty place there. So on occasion, what people do, they take liquid xenon. Liquid xenon is a noble liquid. So on occasion, it is also a scintillator, a good scintillator. And it is a transparent liquid for photons, yeah? So the first thing one can do with the liquid xenon, if we take a barrel of this liquid xenon, a dark matter particle depositing energy in it would make it scintillate. So we put photomultipliers, you see on the top and on the bottom, these tubes here, these are photomultipliers. So we can look at the pulse of light. Then next thing is that imagine that, well, of course, the energy of dark matter particle is larger than the energy of ionization of a xenon. So there will be an electron freed, or a bunch of electrons freed from a bunch of xenon atoms or molecules. This I don't remember. So then this, by the way, the size of this detector is quite large. It's not like in CCD, the pixels are tiny, right? This is maybe meter by meter or something like this. So these electrons are deposited in the middle of nowhere in the volume that is meter by meter. We need to feel a pulse of current from them, right? How would we do this? Here, the fact that xenon is a noble thing helps, because if we apply a voltage between top and bottom, yeah, so these electrons that were liberated in some spot, they will tend to shift a little bit toward, they move toward cathode or anode. So one thing with plus is called cathode, anode. The thing with minus is called cathode. Yeah, the layer with minus. Yeah, so they move away from the production site, but then of course in whatever material they always try to insert themselves back into the atoms, right? They don't like to be free. But if this is xenon, so all the atoms are, all the atoms are complete, yeah? So the layer is filled. They knocked into the next atom, tell that, look, do you have space for me to insert? That's no, go away. So it goes to the next atom, there is no space, so they drift, right? So if we look inside this volume, there is an electron produced here. Of course, the electron would not go straight away because it would bump into the next atoms, right? So it would do sort of a random walk through the detector. It would go to plus, right? Because it is attracted to the plus side. So it would drift with some characteristic drift velocity, but never disappear, right? Because it is difficult to recombine with an atom, right? And finally, it will reach the top of the liquid, well, the surface of the liquid xenon, right? And then actually it can be sampled by what is called, well, it's like a capacitor, right? So there will be finally a pulse of current. There is also a technical detail here, by the way. This barrel is not filled to the very top, and actually the plus is, sorry, my sketch is running out of space here. So there is also a gaseous xenon here, yeah? So what happened when the electron is out of the liquid, it is so happy that it is out that it can move almost freely. It starts to get accelerated by the potential difference. When it is accelerated, it would bump strongly in the next xenon molecule that it finds in the xenon gas, and it would ionize it, right? So then the next, the electrons that are liberated through this ionization would be accelerated again. They would ionize more xenon and so on. So they will be sort of an avalanche produced in the gas phase. And then this is the way to see, to sort of amplify the current pulse, right? Because the number of electrons that would reach the anode will be larger than the number of electrons that went out of the liquid xenon. So the whole technology, again, for those who would do particle physics, the technology is called, it is widely used in particle physics. It is called time projection chamber, TPC. And it's called dual phase TPC because there is liquid and then there is gas phase. In particle physics experiments, these time projection chambers are used as trackers. I don't remember, it is in one of the LHC experiments, the tracker is a time projection chamber. Maybe a side comment like this. So why is it called time projection, by the way, and why would it work as a tracker? If I shoot a muon through this volume, imagine like this, yes, it would cross the whole volume. It would produce electrons all over its way. So all these electrons will start to drift, right? And then, well, first I would see a flash of light also when the muon passes. So I know that, oh, I should expect some current. And then what passed through the detector, I would know through the pattern of the current that I receive. So if it was a muon, I would first receive, again, everything is pixelized here, right? So I would first receive a pulse of current on this side of the detector, right? Then with a bit of delay in the next pixel, with a bit of delay still in the next pixel, right? So measuring the time delay between the pulse of light and the time of arrival of the pulse of current, I can see how the trajectory of a particle went through the detector. I can really trace it. And well, we get a feeling why it is time projection, huh? Because the time delay depends on the projection of the particle on the y-axis of the detector, or z-axis of the detector, right? If my particle is horizontal, the time delay between all the pulse currents is 0, right? If the particle is vertical, I would get 1 pixel shooting, but for a longer time, right? So we can see that, well, this pattern of pulse currents can tell us about the trajectory. So in LHC experiments, perhaps there is a collision point somewhere here. There are bunches of particles going through the detector, and they can actually make a nice picture of all the particles coming from the collision point, right? But here we use it differently. we want to see, well, all these tracks of particles passing through the volume are not interesting for us. We are interested in the most boring possibility that there is one energy deposition in the middle of nowhere inside the volume of the detector. Yes. So, good. Yeah, this is so I scroll through the this because I explained this. And then maybe, yeah, we before the making the break, let's do a small calculation. How does it work? So if I want to predict a number of interactions of dark matter particles within some exposure time, what do I need for this? First, of course, I want to know how many particles are passing through my detector per unit time. This I know because I can measure, well, I can predict from this astronomical data that we were looking at the recap of the previous lecture. We were looking at this rotation, well, something that is derived from the rotation curve of the Milky Way galaxy. We can predict the flux of dark matter particles. This is the first equation. The flux is the density of the particles. Oh, this is mass density divided by the mass of the particle times the velocity, right? So the density is measured in 1 per centimeter cube. Velocity is measured in centimeter per second, right? So it's the flux is number of particles, dimensionless thing, passing through every centimeter square per second, right? Per centimeter square per second. So this is the combination that we need. Now, if I want to know what is the number of particles that have entered my detector within 1 second, I would just multiply the flux by the geometrical area of my detector. Let us assume that the detector is spherical. That's the typical assumption that we do for first back of the envelope. Well, the physicists are always talking about spherical cows, yeah? Because if we start to do modeling, even a cow, which is a complicated thing, we would first assume that it is spherical for simplicity, yeah? That's a joke. Yeah, so I multiply it by r square to have an area. Then this will be the number of dark matter particles that entered the detector within a second, yeah? Now, of course, not all of those particles have interacted inside the detector. I need to know what is the fraction of the particles that have a chance to interact. So I want a probability for a particle to interact inside the detector. How do I estimate it? I need to, well, of course, if my detector is larger and larger and larger, the probability is, is increasing, right? So it is proportional to the size of the detector. More precisely, it is the ratio between the size of the detector and the distance to the next interaction, yeah? So if my size is the distance to the next interaction, my probability is around 1, yeah? The distance to the next interaction is called mean free path. And it is defined like this. Mean free path is 1 over the cross section times the density of the detector. So the cross section is of interaction between particles, right? It is cross section. It is measured in centimeter square. Density is 1 per centimeter cube. So mean free path is something which is measured in centimeters. I divide the size of the detector by the mean free path to get the probability. It gives me the number of interactions per unit time. This is this formula. Now I added a lot of subscripts to indicate what is the nature of, say, the cross section is the cross section of interaction of dark matter with detector. Yeah, that's why I write it like this. That is more evident. Okay, so if I'm exposing the detector during some time interval t. I would just multiply this by the time interval. This is the number of interactions per exposure time. Then, of course, what do I see in this formula is that well, this if I compare the previous formula with this formula, I re-expressed the number density of detector as the density divided by mass of detector particles. For simplicity, I took proton mass, right? And then number density times the volume is the total number of particles of detector, right? So it depends on the mass of the detector. If I multiply total number of particles by the mass of every particle, it is the mass of the detector, right? So a good dark matter detector is a very massive thing. Yeah? So the larger is the mass, the better is my chance to see something. Of course, there are some limitations. If I take a bigger and bigger detector, I am looking for some tiny interaction within the volume, right? So it gets more and more difficult to spot this interaction, right? So there is always a trade-off. Either I take a huge detector, but then the bump inside the detector should be also huge so that I see it from far away, yeah? Or I take smaller pieces and then I attach sensors to every piece, and then I can get to larger mass by piling up this stuff, right? So in this xenon detector, people decided that no, we go to large volume, yeah? The latest version of the detector is called xenon 1 ton. They are building a detector that is called xenon n-ton, yeah? So a much larger thing. They even cannot tell how heavy is the detector, right? So it's n-ton. And there is a bunch of detectors like this. Some of them use xenon, some of them use another noble gas called argon, yeah? And in Switzerland, there is a big group in Zurich, and there are two in Bern also. There is a group operating this liquid xenon TPC. Yeah, the detector itself is in the highway tunnel in Italy. It's called Gran Sasso. Somewhere, it's near the town of L'Aquila. I don't know. Maybe you are maybe too young to remember that there was a huge earthquake in Italy some time ago that nearly destroyed this nice town of L'Aquila. So Gran Sasso is next to this town. Actually, there is a Gran Sasso Institute that is in L'Aquila itself. Okay, so let's make a break maybe. I would change the topic now. Let's make a break of 10 minutes. So we come back at 9:27. Good. Yes.
The energy is like these. It's we have closed system and do we have the change of mass?
No, there is no change of mass. The mass is no, this is rho is the energy density, right?
So Yeah, I see.
Good.
Thank you.
So we are back. Maybe we can close the door. And the camera is working for those on Zoom. It was the problem of battery remote control. Okay. Slide, here it is. Yeah, so maybe to finish this story of dark matter detection, if we know, in this formula, we take a detector of largest possible mass, as I told, xenon 1 ton, or maybe, I don't know how far they are going to go. So the velocity of dark matter particles we know, the density of them we know from astronomy. So if we measure something, if we see events, we can measure the cross-section of interaction of dark matter particles, right? That's what we would derive. If we don't see the signal, we would rather tell that, okay, we tried to do our best, but we don't see anything. So this means that the cross-section of interactions of dark matter particles with conventional matter is below some limit. Yeah, that's what experiments do. Now, you can guess that there were no press releases or, well, there were no Nobel Prizes for discovery of dark matter. So up to now, all the searches with this method, it's called direct detection method, were unsuccessful, right? So the only thing that we can tell is that the dark matter cross-section cannot be too high, yeah, too large. That's how people present their results. So the limit on the cross-section, it in fact depends on the mass of the particle. We can quickly try to understand the shape of this plot. So everything that is colored is excluded by one experiment or the other. On occasion, you see this, well, our friend Xenon. Before it was Xenon 100 kilo. Now it is Xenon 1 ton. And well, the next generation would be Xenon N ton. And then, well, the other experiments, I don't go into the details. So first thing to notice is that when we go to lower dark matter masses, the limits get worse. That's obvious thing, right? Why would this be like this? What do you think? Think about the method itself.
The energy.
Yes, the higher the is, well, the higher is the mass of dark matter particle, the higher is the kinetic energy, right? Because the velocity is fixed. It's 200 kilometers per second, yeah? So the kinetic energy of smaller mass particle is lower. The smaller energy deposit is more difficult to detect, right? There are less photons from scintillation, the pulse current is weaker, and so on, right? So at some point, this becomes insufficient for detection, yeah, the signal. That's why the limit has to go bad below some threshold, yes? Now, if we go to higher masses, the limits get worse gradually. Why would this be like this? Let's try to check. If we look at 100 GeV mass, the limit is somewhere in whatever units, 10 to the minus 46. If we go to 10 to the 4 mass, GeV mass, the limit is 10 to the minus 44. So we go up 2 orders of magnitude in mass, and the limit worsens by 2 orders of magnitude. What is the effect here? Try to look at this formula. Do you see it? The last formula on this page. What's the idea here? Where is the mass of dark matter particle? in the last formula? Huh?
MDM.
MDM, where is it? In denominator, right? So what are we detecting? We're detecting a number of events, yeah? So if we don't detect any event at all within, well, a year of exposure, right? We tell that, okay, we didn't detect any. We expect that, well, if there is some rate of events, their arrival statistics follows Poisson distribution. So we tell that perhaps if we didn't detect any events, this means that within this time, at the confidence level, I don't know, 95%, there might have been at most 3 of them. If we would repeat experiment more and more times, sometimes we would still find an up fluctuation at 3 events. That's the specific of the Poisson distribution, right? But it will be only in 5% of cases, something like this, yeah? So we tell that, so the number of, the maximal possible number of detected events would be 3, right? And then we would express but yeah, if these 3 events for a dark matter particle of 100 GeV mass would mean, so this sigma divided by n is a fixed thing, right? So then my sigma would, if I would express sigma from this formula, it would scale proportionally to m, right? The bound on sigma would scale proportionally to m. This is the origin of this rise here on the right, yeah? So qualitatively, all the results look the same. You see, if I take xenon experiment, it has this linear dependence up to, say, 30 GeV mass, and then it gets worse, yeah? Because this is the sensitivity limit of, well, this is, at left, it gets worse at some energy threshold. If I take, what do I take? I take this dark side 50, it's an liquid argon experiment of 50 kilogram. The limit gets worse, is linear up to 100 G electron volt, but then it gets worse a bit at high energy because the energy threshold is higher. But all the curves are more or less the same, yeah? And then, well, it's not very exciting, say, life, right? When you are looking for years, you are trying to construct more and more sophisticated detectors, and you never detect anything. That's a bit sad, but for them there is light at the end of tunnel, maybe a reward. Even if they don't detect finally the dark matter, you see there is some nice orange line, it's called new floor. So finally, they would be sensitive to the cross sections that are as small as cross sections of neutrinos of some energy. Well, actually, they are detecting EV recoils, right? But they can also detect MEV neutrino recoils. Yeah, that's the energy of neutrino is not GeV, but there are a lot of neutrinos coming from the sun that have energies in MEV range. And even though their cross-section is tiny, but the experiments will be so sensitive that they will start seeing some signal, right? It's not the signal that they are searching for, but it's a byproduct. So maybe they will start to do some other type of physics with the increase of sensitivity. One sad thing to notice about this plot is that you remember this estimate from cosmology. If I go to the first page here, our estimate was that we want an annihilation cross-section of dark matter particles that is about 10 to the minus 25, 10 to the minus 26, if I multiply it by V, right? Suppose that it's divided by even C, yeah, speed of light. I divide by 10 orders of magnitude, so it's 10 to the minus 35, yeah, or something. Here, the limits are at the level of 10 to the minus 45. Yes. So we are already past some natural scale. Yeah. Of course, it is a subtle thing, right? There I'm looking at annihilation cross-section, and it is annihilation into anything, right? Here we are looking at some one possible channel of interaction. It's not scattering of dark matter into anything, right? We are looking for elastic scattering, yeah? It's one of the channel of the reaction. So there is a story of when reaction can go into different outcomes. It's called branching ratios, right? So there are models of WIMP's dark matter. They are typically derived from some supersymmetry theories and so on. So this is still natural for supersymmetry, but let's say from naive pedestrian point of view, this is a bit discomfortable. Like say the difference of 10 orders of magnitude in cross section, it's a bit already. So the experiments are very sensitive, but well, the chances that well, the dark matter is really WIMPs is maybe disappearing. Yeah. Well, maybe I'm too skeptical because I'm outsider, right? If I would be part of their team, I would be super excited by this incredibly sensitive experiments. Some of them are really excited, by the way, of those people. You see, there are two islands here called Dama 1 and Dama 2, Dama 1 and Dama natrium. Yeah. This is a team which also runs an experiment in Gran Sasso, but it's on a bit different technology. It's a bit like this CMOS camera, but well, they use semiconductor, not silicium, but germanium, to sample pulse currents. And they run in the same laboratory in Gran Sasso, and they, since years, claim that they see a signal. Even they don't do these multiple techniques here, it's a sophisticated machine. It detects pulse currents and light. There they detect only pulse currents, but they are confident that they see something fundamentally right. The experiment Dama, nobody believes them, by the way. But well, it's again, well, I'm recorded on well, I will not put it into the public domain because it's not very, say, politically correct statement, right, for the Dama team. But let's say there are they claimed long time ago that they see the signal of dark matter, and they insist. And actually, there are experiments that are trying to repeat their method, and well, a bunch of experiments that try to reproduce their result with different materials. They failed, but they all see some anomalies. That's some overview of attempts to repeat Dama, but well, I will not go into details here. But well, to tell what is the Dama story is well, it's a useful thing useful element of dark matter detection method. What Dama does, it tries to see some peculiarity of the signal. They cannot clean their signal to make it background free. I told in Xenon they do, well, they don't see events, so they tell that there are no more than some 1 to 3 events per year. Yeah. So here in Dama, they have a lot of events because there is a lot of background that they do not know how to reject. But they see an effect that is called annual modulation effect. This annual modulation, it works like this. So now we need to go a little bit back to astronomy, right? So let's look, this is sort of a sketch of our galaxy. It's of course not our galaxy because we are inside, right? We don't have a view like this, but it's perhaps, it's not an AI, it's a real artist who did the sketch, right? But so, okay, so we are sitting somewhere in the galaxy and the galaxy rotates. So the sun moves around the galactic center with velocity 200 kilometers per second. The dark matter particles, they don't follow this rotation. They are virialized, so they move in whatever directions. Actually, the particles that are coming from this side, well, suppose that we move in this direction, yeah? So the particles that are coming from this side, they come with a little bit higher velocity, right? So the flux is a bit higher, the head-on than the tail-in flux, yeah? This is a fact that people routinely take into account, that's okay. But there is more of this effect. If we look at the solar system itself, the Earth rotates around the sun with velocity 30 kilometers per second. So if we look well, I'm not sure if this orientation is exactly like it should be, right? But if we look at one moment of time at the rate of events in whatever dark matter detector, we measure it, and then we repeat a measurement a half a year after when we are on the other side with respect to the sun. So on one side, our speed of motion around the sun adds to the overall speed of the sun motion through the gas of dark matter particles. And on the other side, it subtracts, right? So sometimes we are moving through the gas of dark matter particles with velocity, well, 230 plus 30, and sometimes 230 minus 30, yeah? Overall, it makes a sizable thing, right? It's plus minus 13% or something. And we even can predict, we know what is our the orientation of the solar system with respect to the sun motion in the galaxy, right? So we can even predict that, say, in June, the flux is higher, in December, it's lower. And that's what this DAMA experiment sees. This is the theoretical prediction. This is the flux variation over some 20 years or so. They keep the experiment running till today. They never fail, so it's systematically sinusoidal. And well, this sinusoidal implies that this annual modulation effect implies that the dark matter should have the cross-section that is like this. That is, by the way, closer to the natural expectation, yeah? Well, so again, I'm not insider in the field. I know that other experiments are trying to repeat it. The most recent one is called like this. So this is the amplitude of annual modulation observed by DAMA, like 1% or something. Then the amount of, this experiment uses exactly the same germanium crystals as DAMA. And they don't see the modulation at any energy at which they measure. While they are accumulating exposure, sooner or later they will also either rule out DAMA or confirm it. Well, the statement of this DAMA collaboration is that maybe the fact that they see it and other experiments don't see it tells us something interesting about peculiarity of interaction of dark matter. Maybe the dark matter is germanophilic, yeah, because the material they use is germanium, right? So they like German, they don't like French, right? Maybe like this. They are sort of, it's like in Switzerland, we can be more favorable to Swiss Allemand than to Patois Roman, right? Something like this. So it's a story that is still in development, okay? That was a comment on, yeah, so this is the state of art in direct detection of dark matter. Maybe in the remaining 15 minutes, I will make a comment like this. As I told, this story is an example, right? People are trying to, what is the logic here? So somebody proposed a theoretical model of this better neutrino that can make a dark matter. And then this theoretical model challenges astronomers. They try to see signatures of this better neutrino, which is WIMP, in astronomical data. People try to do, other type of physicists try to do laboratory experiments, right? If there is another model of dark matter, maybe there is another way to test it astronomically or do another experiment. Well, this would be nice, except for the fact that there are so many of these dark matter models that the chance that, well, some of them are testable in laboratory is very low. Yeah. When these direct detection people publish their results, they mention that our constraints can be reapplied to one type of the model or another type of the model. Recently, they also started to publish their data. I propose to Volodymyr to give you like optional exercise if you want to try. These xenon data are public, right? Why do they make them public? They encourage theoreticians to go like this. If you have your favorite model of dark matter, maybe it should have a signature in our detector. So predict what you need to predict is the spectrum of these nuclear recoils, and then put it through our data analysis software. You can constrain your model of dark matter. Then this works in a limited way because, well, there are obviously dark matter models that would not produce any signature in their detector. The most dramatic one is on the right. I was not able to squeeze it into the energy because, for example, dark matter can be made of small black holes, right? How would we detect them? Every black hole can be even a solar mass black hole. Maybe our galaxy is full of solar mass black holes. They would obviously, their density is ridiculously low. The density of these GeV particles is 1 particle per 10 centimeter cube. We can catch them in laboratory, right? But if these are solar black holes, we know, well, our distance to the next star is about 1 parsec, right? That should be, we know that around us, the density of normal matter and dark matter is the same. So if we mix just the same amount of black holes as stars, right? 50-50, that would do the job. Do we have a possibility to detect a solar mass black hole in xenon? No. Yeah, so that's the problem with the direct detection experiments, that they would never be a universal thing, right? So they cannot tell us something that is, well, the technological capabilities of mankind are rather limited. So this brings me to another possibility. I'm coming back to astronomy, right? It's the same energy axis as before. So in the previous slide, this was the energy axis. That was rest energy of dark matter particles, yeah? I, by the way, occasionally wrote another axis below, which is frequency, because in natural system of units, we can convert energy into frequency, right? On occasion for photons is just the relation between the frequency and energy. Well, let's look at the photons. So for photons, we have learned over the years how to detect photons of over a wide energy range. For astronomy, we use photons with energies 10 to the minus 6 electron volt up to 10 to the 15 electron volt. Or moreover, recently we have learned how to detect other types of signals from astronomical sources. We can use cosmic rays or neutrinos nowadays. Then this extends our range up to sort of 10 to the 20 electron volt. And most recently, we also know how to detect gravitational waves. Those are, we know how to detect them with frequencies down to 1 oscillation per year. That would be a nanohertz frequency. So in astronomy, maybe our range of possibilities to find imprints of dark matter onto some observable effect, we are better off, maybe, yeah? Coming back to the same black holes, there is a simple prediction that this would be dark matter black holes. We know that half of the systems in, half of the stars in our galaxy are in binary systems, yeah? We should assume the same. This is statistical thing, so when, well, perhaps these black holes were produced somewhere in the early universe close to each other, Some of them would occasionally be bound into binary systems. If this is like this, they turn one around the other, lose energy, and finally come closer. And well, we know that the ultimate shortest possible period for two black holes of solar masses turning one around the other is in the kilohertz. So this is the, well, our period of rotation around the sun is 1 year. If we use the formula of Kepler, we move the second body close to the surface of the black hole, the period of rotation would be millisecond, okay? So a prediction of that model is some observational effect, right? There should be black hole spinning one around the other with kilohertz frequency or millisecond period. They should produce a lot of gravitational waves. So we would use these gravitational wave detectors to constrain the possibility that the dark matter is made of black holes. This is already done, by the way. Well, the most recent data of gravitational wave detectors tell us that these solar mass black holes, or maybe 10 solar mass black holes, cannot do the job, right? So they cannot make the total of dark matter. So we can be inventive and try to find constraints on dark matter using astronomical methods, right? So this brings me to the astronomy, back to astronomy, and I want to illustrate how does it work on example of gamma rays. I'm coming back to this WIMP story. So WIMPs are 100 GeV particles, and on occasion, as I already mentioned in the previous lecture, we can use gamma ray telescopes, or we can look at cosmic ray detectors. You remember there was this electron-positron. Well, that's there was this story of positrons. Something is wrong with positrons in the cosmic ray in the spectrum of cosmic ray positrons. Yeah. But well, I will pick the gamma rays, and well, I already have shown this plot last time, right? So we know the density profile of dark matter in the Milky Way. The most popular one is this blue one called Navarro-Frank-White. Around the sun, we have this 0.3 GeV. Well, the sun is this at 8 kiloparsec. We have 0.3 GeV per centimeter cube. This is equivalent to sort of 10 to the 8 solar masses per kiloparsec, whatever it is. Then, as I told, we can predict that these particles, the density grows in the center of the galaxy. And finally, it grows to such an extent that dark matter particles start to bump into each other. When they do this, they would disappear and produce particles of standard model of particle physics. Among them will be photons. Actually, well, they would, anything that they produce will result in photons ultimately. And this should make, the prediction is that this should make the center of the galaxy glow in gamma rays. So of course, people simulate this. Well, we made a small calculation last time that the brightness profile should scale as 1 over the distance to the center of the galaxy square. So it's a bright source right in the center of the galaxy. In this map, you see more features. These are nearby galaxies, by the way. They would be much weaker than our own galaxy. Yeah? This is a clear experimental or observational prediction. We should look in the gamma ray telescope, right? We do this. You will perhaps do this in the exercises, and oops, well, maybe there is a signal of dark matter. I missed, by the way, the center of the galaxy. Sorry, I displaced occasionally the map. The arrow was pointing right to the center of the galaxy. I know where is the center of the galaxy. It's at the, well, it's over there, right? But it's not the signal that I was looking for. There is a lot of garbage around. And then this shows the difficulty of astronomical methods. It's a generic difference between astronomy and laboratory experiments. In astronomy, in laboratory experiments, we design our experimental setup in such a way that it is well controlled. if there is a tiny deposition of energy in the middle of xenon detector, we would spot it and we will characterize it and we will tell that, yes, this is the dark matter particle interaction, right? Here, there might be lots of dark matter particle interactions in the center of the Milky Way, but go and find them. There is some unrelated stuff there, yeah? So we cannot change anything here because we cannot remove, these unrelated sources. We cannot improve our detector, which is the Milky Way galaxy, to make it more suitable for dark matter search. We have to cope with this, right? So instead of removing backgrounds, we need to control them. What does it mean to control them? It means to do astronomy. So we should stop being dark matter searchers. We should start being good astronomers. Means that, well, it's a nice thing. Astronomy is an interesting domain of science, right? So the thing that is background for dark matter physicists is an exciting signal for astronomer. And then maybe I have 2 minutes left. I will scroll through this map just to give you an impression. Next time we will go into astronomy. And I will introduce you. Well, today we are on the point of view of dark matter searcher. So I will show you what kind of backgrounds do we have in this map. Next time I will change my, I will retourner la veste, oui. I will become a passionate astronomer and I will disregard this dark matter signal. But for the moment, let's consider these backgrounds. So the first obvious background that we see, this is, by the way, it was a comment that we can make rather precise predictions, not only for the location of the dark matter signal, but also for its spectral shape. For WIMPs, we can calculate what is the probability of WIMPs to decay into one or the other channel. And then this, the secondary, we calculate the secondary processes that lead to emission of photons. So in fact, we always have a spectrum of emission from these WIMPs. This we can measure with telescopes as well. So spectrum, I would tell that we can have a whole data cube in astronomy, right? We can have image in every energy band. Yeah, this would make us, we can fit this image in every energy band to the model that we use, that we have. Okay, so then for the background, one obvious thing is that the disk of the Milky Way is glowing. The disk of the Milky Way is glowing as a whole, right? The origin of this glow is that there are cosmic rays that we detect here on Earth. Yeah. But before reaching the Earth, the cosmic rays were produced in some sources in the Milky Way. We don't know which are those sources. They have traveled through the interstellar medium. While traveling through interstellar medium, they were bumping into the interstellar gas made of protons. And typically when a high energy proton or atomic nucleus and bumps into low energy proton, the first thing they like to do is to produce particles that are called pions. These are 2-quark particles. Protons and neutrons are 3-quark particles. Pions are simpler, they are 2-quark particles. But pions decay, and well, neutral pions would decay into photons directly. That's what we see here. So in fact, it's a nice background for, it's a nice signal for astronomers. We can study how cosmic rays are traveling through interstellar medium using this signal. There is even more beautiful thing. If we look at these brightest isolated sources, these are pulsars. So here on this side, it's, for example, pulsar that is called Crab. They look beautiful on the sky. This is a nebula around Crab pulsar. There is a lot of stuff here to study, right? Note that this is a map of a telescope that is made of photons with energies more than GeV. It's on the top left written, it's Fermi telescope. Then, somehow this nebula emits photons with energies larger than GeV. GeV is the rest energy of proton, right? So these photons are generated by relativistic particles, means that somehow this nebula operates a particle accelerator. it's, well, would be nice to know why is it like this, yeah? Then another type of sources are supernova remnants. Again, somewhere here, it's one of the most recent supernova remnants. Well, these are explosions of stars that are also operating particle accelerators. Something to understand for astronomers. This is Cassiopeia supernova remnant. So you see there was a star exploding somewhere here. It left a small remnant, which is a failed pulsar, by the way. And then all the star was was thrown into the interstellar medium. And then outside of the galactic plane, maybe over there or over here, this source is it has a name. We see another type of sources that are called active galactic nuclei. These are black holes in the centers of galaxies that, as we see, they appear on this map, that also operate particle accelerators, right? So in gamma rays, the gamma ray astronomy is the story of particle accelerators working one way or the other in different types of astronomical sources. On occasion, right in the center of the Milky Way, we sadly have also a black hole that might do the same. And this is annoying because that's exactly where we expected the dark matter signal. And suddenly there is this black hole that wants to operate a particle accelerator and doesn't let us detect our dark matter, right? So next time we will gradually go into this subject of what happens, why do, well, how to understand this date of